This is the last and fourth module of chapter 8. This module is divided into two parts. In first part, we discussed about the shooting method to solve boundary value problem. And in second part, we discussed the stability of some numerical methods. In shooting method, a second order boundary value problem is converted to two second order initial value problems, and by solving these two initial value problems and combining the results of these two problems, we obtain the solution of the original boundary value problem. So, this is one of the best method to solve boundary value problem. Let the boundary value problem be second derivative of y minus p of x into first derivative of y minus q of x into y equal to Rx. So, this is a linear second order differential equation with the Dirichlet boundary conditions y at a equal to alpha and y at b equal to beta, where alpha beta are given constant. This problem is to be solved by performing the following three steps. In first step, we convert the given boundary value problem to two equivalent initial value problems. In second step, solve these two initial value problems by any method, for example, say Runge-Kutta method or predictor corrector method or any other method. In third step, combine these two solutions to get the required solution of the given boundary value problem. So, these are the three simple steps to solve this boundary value problem by shooting method. Let Ux be a solution of the initial value problem. Second derivative of u at x minus p of x, first derivative of u at x minus q of x into ux equal to Rx with the initial condition u at a equal to 0, u of a equal to alpha and first derivative of u at a equal to 0. That means the initial condition is taken as this form. Also let Vx be a solution of another initial value problem, second order initial value problem. Second derivative of v of x minus p of x into first derivative of v of x minus q of x into v of x equal to 0. Note that in second problem the right hand side is 0, but in first problem the right hand side is taken as Rx, which is the right hand side of the original boundary value problem. Here the initial conditions are v a equal to 0 and first derivative of v at a equal to 1. So, initial conditions are changed according to the given problems. Now, equation 2 and 3 are the initial value problems, second order initial value problems. These problems can be solved by any method, but the Runge-Kutta method, second or fourth order Runge-Kutta method is suitable to solve equation 2 and 3. The linear combinations of the solutions of equations 2 and 3, that is yx equal to c1 into u of x plus c2 into v of x, is the solution of the given boundary value problem, where c1 and c2 are arbitrary constants and the value of this constant are obtained by the boundary condition y equal to alpha and yb equal to beta. So, for this boundary condition and using equation 4, we have two equations, alpha equal to c1 into u at a plus c2 into v at a equal to beta equal to c1 into u at b plus c2 into v of b, and solving these two equations we get c1 equal to 1 and c2 equal to beta minus ub whole divided by vb. So, this is the important result to get the combined result for the given boundary value problem. Thus, equation 4 finally reduces to yx equal to u of x plus beta minus u at b whole divided by v at b into vx. So, equation 5 gives the value of y when u and v are given. This is a solution of the given boundary value problem and it is also satisfies the boundary conditions y at a equal to alpha and y at b equal to beta. Now, to solve the equation 3 and 4, we substitute u prime x equal to wx, where prime represents the derivative with respect to x, to the first equation, first second order initial value problem. Then it becomes u prime x equal to wx with ua equal to alpha, and the second equation of first problem is w prime x equal to p of x into wx plus q of x into ux plus rx with the initial condition wa equal to u prime a equal to 0. So, this is a pair of first order differential equation of the form dy dx equal to f of xy z, and this equation can be solved by Runge-Kutta method. The second equation is converted into a pair of first order linear differential equation by substituting v prime x equal to zx, then v prime x equal to zx with the initial condition va equal to 0, and the second equation is z prime x equal to px into zx plus q of x into v of x with the condition za equal to v prime a equal to 1. So, equation 6 and 7 are two pairs of initial value problem, first order initial value problem, which is coming from the two second order initial value problems. The shooting method is a very good method to solve boundary value problem because it is free from the generation of system of linear equations. But if the expression p of x into first derivative of y at x plus qx into y of x plus rx is linear, then there is no problem. That means the problem is very simple. But if the expression, the same expression is non-linear, then a lot of iterations are required to get the solution at x equal to b. X equal to b means the right bound of the problem. When y at b is a very sensitive, then it is very difficult to obtain the convergent solution for nonlinear case of the expression. In this situation, the integration may be done from the opposite directions by guessing a value of y prime b, and the iteration be repeated until y a is sufficiently close to the initial value y 0, and the speed of convergence depends on the initial guess or the value of y prime b. Now, we consider one example to illustrate the shooting method. This is the second order boundary value problem with the boundary condition y at 0 equal to 0 and y at 1 equal to 1. That means the boundaries are 0 and 1, and the values of y at 0 and 1 are 0 and 1 respectively. Now, we use the second order Runge-Kutta method to solve the initial value problems by taking h equal to 0.20. For this problem, p of x equal to x square, q of x equal to minus x plus 1, r of x equal to 1, and the boundaries are 0 and 1, a equal to 0, b equal to 1, and the boundary values, that means alpha equal to 0 and beta equal to 1. The two initial value problems are, the first one is u prime equal to w with u 0 equal to 0, and second equation is w prime equal to x square w minus x plus 1 into u plus 1, and the initial condition is w 0 equal to 0. And the second problem is v prime equal to z with v 0 equal to 0, and second one is z prime equal to x square z minus x plus 1 into v, and the initial condition on z is z at 0 equal to 1. So, these two pairs of equation can be solved with the help of second order Runge-Kutta method. The first equation, first pair of equation, that means the system of equation 8 is solved by Runge-Kutta method, second order Runge-Kutta methods, and the solutions are given by this table. The last two column gives the values of u and w for different values of x. That means the u1 is 0.02000, u2 is 0.07984 and so on, and the last value, that means the value of u5 is marked in red color. That means the value of u at 1 is equal to 0.48842. This value is required to find the value of the constant C or C2. Similarly, the last column represents the value of W for different values of X. Similarly, the second order Runge-Kutta method is used to solve the system of equation 9, and the solutions are given by this table. The last two columns represents the values of V and Z for different values of X. Note that the blue mark value, that means V5, represents the value of V at x equal to 1, and the value is 0.83549. And the last column represents the values of Z1, Z2, Z3, Z4 and Z5 for different values of X. The value V5 is also required to evaluate the constant C2. To find the solution of the given boundary value problem, we can calculate the constant C, that one is mentioned in the theories as C2. The C equal to beta minus UB whole divided by VB, which is equal to 1 minus U1, in this case B equal to 1 whole divided by V1, equal to 1 minus 0.48842 whole divided by 0.83549. After simplification, the value of C becomes 0.61231. So, using this value, the value of Y are given by the different values of Y at different values of X are given by Yx equal to Ux plus C into Vx, which is equal to Ux plus 0.61231 into Vx. And the values of X for different values of X are given in the following table. The first row represents the values of X, that 0.2, the values of U is 0.02, value of V is 0.20, and using the formula, above formula, the value of Y is calculated as 0.14246. Similarly, this is the values of X, U, V and Y. These are the values of UV and X, UV and Y, and these are the values of UV and Y for different values of at the values of x equal to 0.8, and last column represents the U when x equal to 1, third column represents the value of V at x equal to 1, and last value is the value of Y when x equal to 1. Note that the last value, that means the value of Y when x equal to 1, which is exactly equal to the value of upper boundary of the given boundary value problem. So, this is the solution technique of shooting method, and note that this method is free from generation of recurrence relation or free from the generation of system of linear equations which appears in finite difference method. The shooting method is described to solve a second order boundary value problem, and in this method the given boundary value problem is converted to two pairs of initial value problems, and these two pairs of initial value problems can be solved by any methods like Runge-Kutta method, second or fourth order methods, and by any other methods. We obtain the solution of the given boundary value problems. This method can also be extended to solve third order boundary value problem by converting the given equation into three pairs of initial value problems, and so on. Now, we consider the stability of some numerical methods which are described in this chapter. The stability analysis is one of the important part of the numerical methods to solve ordinary differential equations. Without loss of generality, we assume that the model initial value differential equation be this one, dy dx dy dt equal to lambda into y, where x equal to 0 and y equal to y0, where y0 is a given constant, and the parameter lambda is a real or a complex number. It is obvious that the solution of this equation, that means equation 10, is y equal to e to the power lambda t into y0. This is obvious solution. We assume that lambda equal to lambda r plus I into lambda I, where lambda r and lambda I are the real and imaginary parts of the parameter lambda, and it is assumed that lambda r is less than or equal to 0. If this quantity is positive, then the solution converges to or goes to infinity. So this is the very important assumption for this initial value problem. Similar to the differential equation, let us consider the following model linear initial value difference problem. That means yn plus 1 equal to sigma into yn, where n equal to 0, 1, 2 and so on. Here y0 is a given, that means this is called the initial condition for y, and sigma in general is a complex number. And the solution of this difference equation, that means solution of equation 12, is yn equal to sigma to the power n into y0. And it is obvious that if the absolute value of sigma is less than or equal to 1, then the solution remains bounded. Otherwise, it goes to the infinity when n is very large. Now, to connect the exact solution and the solution obtained from the difference equation, we determine the exact solution at different values of t, that means at t n equal to n into h, for n equal to 0, 1, 2 and so on, and h is any positive number. This is called the step length. Then yn equal to e to the power lambda into tn whole into y0. This is equal to e to the power lambda into nh into y0 equal to lambda sigma to the power n into y0, where sigma is taken as e to the power lambda h. The exact solution, that means the solution obtained from equation 14, will be bounded if the absolute value of sigma equal to the absolute value of e to the power lambda h is less than or equal to 1. And it is possible if the real part of lambda h, which is nothing but lambda r into h, should be less than or equal to 0. It is obvious from the equation, if the real part is less than or equal to 0, then the solution yn converges to 0 for large n. In this diagram, the stability region for exact solution is shown by green region. That means that stability region for exact solution is the left half part of the imaginary axis im lambda z, and within this region the exact solution remains bounded for any values of lambda h, where lambda h lies in this region. Now we consider a particular case, that means the Euler's method, that means the stability of Euler's method. The model differential equation 10, for this model equation, the value of yn plus 1 obtained by Euler's equation or Euler's method is given by equation 15. That means yn plus 1 equal to 1 plus lambda h into yn. So this is nothing but a difference equation, and by solving this difference equation we get the solution yn equal to 1 plus lambda h whole to the power n into y0, which is equal to sigma to the power n into y0, where sigma equal to 1 plus lambda h. And by previous argument, it is obvious that the method is stable or the solution is stable if the absolute value of sigma is less than or equal to 1. So this is the sufficient condition for stability of Euler's method. In general, the parameter lambda is a complex number. Now we consider different values or different type of values of lambda to study the stability of Euler's method. In case 1, we assume that the parameter lambda is purely real number. So in this case, the absolute value of sigma, that means absolute value of 1 plus lambda h less than 1, or after simplification it becomes minus 2 less than lambda h less than 0. That means if lambda h lies between minus 2 and 0, then the numerical solution obtained by Euler's method is stable. If the lambda is purely imaginary, then we assume that lambda equal to iw, where w is a real number. In this case, the absolute value of sigma, that means absolute value of 1 plus lambda h, that is absolute value of 1 plus iwh, equal to square root of 1 plus w square into h square. Obviously, this quantity is greater than 1. Therefore, we conclude that the method is not stable in case of lambda is purely imaginary. In case 3, we assume that the lambda is a complex number, that means it has a real part as well as imaginary part. So, we assume that lambda equal to lambda r plus I lambda I. In this case, the absolute value of sigma equal to absolute value of 1 plus lambda h equal to square root of 1 plus lambda r h whole square plus lambda I into h whole square. It can be less than or equal to 1 for suitable values of lambda r h into lambda I h. That is, lambda h lies inside the unit circle. That means, if the values of lambda h lies within the unit circle, then this method gives a stable solution. Now, we represent all these cases in this diagram. That means, inside of the circle 1 plus lambda r into h whole square plus lambda I h whole square equal to 1. This represents a unit circle whose center is minus 1 0 with radius 1, and this circle is shown in the following figure, and this is marked by blue color. So, within this region, within this unit circle, the Euler's method gives a stable solution. That means, if we choose the value of lambda h in such a way such that the value lies within this unit circle, then surely Euler methods gives a stable solution. Now, we conclude that to get a stable numerical solution by Euler's method, the step size h must be reduced such that lambda h falls within the unit circle. So, this is the main objective of the stability analysis of any method. That means, the stability analysis actually determines the maximum value of the step size h. Now, if lambda is a real and negative, then the maximum step size for stability is 2 by absolute value of lambda. That means, h less than or equal to 2 by absolute value of lambda. If lambda is real and the numerical solution is unstable, then obviously the value of absolute value of 1 plus lambda h must be strictly greater than 1. This means 1 plus lambda h is a negative number with magnitude greater than 1. So, in this case, if the value of 1 plus lambda h is negative and its magnitude greater than 1, then the Euler's method gives an unstable solution. Since yn equal to 1 plus lambda h power n into y0 for Euler's method, the numerical solution exhibits oscillation with changes of sign at every step. Now, let us consider second order Runge-Kutta method, and we shall discuss the stability of this method by considering the different values of lambda. Now, first we calculate the values of the parameter k1 and k2, which appears in the formula in second order Runge-Kutta method. For the given model differential equation, k1 is equal to lambda into h into yn, and k2 is lambda h into 1 plus lambda h into yn. Using this value, the value of yn plus 1 is yn plus half of k1 plus k2 equal to yn plus lambda h whole to the power 2 by 2 whole into yn. After simplification, it is equal to sigma into yn, where sigma equal to 1 plus lambda h whole to the power 2 by 2. So, this is the value of sigma, and for stability this value should be, absolute value of sigma should be less than or equal to 1. Now, we consider different values of lambda. In case 1, we assume that the value of lambda is real, like previous case. In this case, 1 plus lambda h plus sigma square into h square by 2 is less than or equal to 1. After simplification, this equation or this inequality becomes minus 2 less than equal to lambda h less than equal to 0. So, if the value of lambda h lies between minus 2 and 0, then the second order Runge-Kutta method gives a stable solution. If lambda is purely imaginary, that is if lambda equal to IW where W is a real number, then the absolute value of sigma is greater than 1, then we conclude that in this case the method gives unstable solution. Now we consider lambda as a complex number. In this case also the sigma equal to 1 plus lambda h plus lambda square h square by 2, and which is taken as e to the power I theta, where theta is a real number and I is the complex number, that means root over minus 1. Now we find the complex root lambda h of this polynomial for different values of theta. It is easy to verify that the absolute value of sigma equal to 1 for all real values of or for all values of theta. Obviously theta is a real number. Now this is the diagrammatic representation of the stability region of second order Runge-Kutta method. The inner region represents the stability region of second order Runge-Kutta method. Note that the inner portion bounded by along the real axis minus 2 to 0, and along the imaginary axis the lower bound is minus root over 3 and upper bound is root over 3. Now we consider fourth order Runge-Kutta method to analyze its stability. For the model differential equation, the values of k1, k2, k3 and k4 are calculated here, and using this value, the value of yn plus 1 is given by this expression. In this case, sigma equal to a 4th degree polynomial, which is nothing but 1 plus lambda h plus 1 by factorial 2 lambda h to the power 2 plus 1 by factorial 3 lambda h power 3 plus 1 by factorial 4 lambda h whole to the power 4. So this is the expression for sigma, and for stability the absolute value of sigma must be less than or equal to 1. For different values of lambda, the stability of fourth order Runge-Kutta method is discussed below. For real lambda, the value of lambda h lies between minus 2.785 to 0, and in case of purely imaginary lambda, the value of lambda h, the absolute value of lambda h lies between 0 and 2 into root 2. In case of complex lambda, the stability region is obtained by finding the roots of the fourth order polynomial with complex coefficients. So this is the fourth order polynomial, and right hand side is taken as e to the power I theta, where theta is a real number, and note that lambda h is a complex number, so it is a complex polynomial of degree 4. So this is represents, that means the outer region represents the stability region of fourth order Runge-Kutta methods. The entire region represents the stability region for the fourth order Runge-Kutta method, and it indicates that the region of stability of fourth order method is significantly larger than the second order Runge-Kutta method. That is, the step length h in fourth order Runge-Kutta method may be taken as larger than the second order Runge-Kutta method. And note that the region is bounded along the imaginary axis is bounded by minus 2 root 2 to 2 root 2, and along the real line the bounds are minus 2.785 and 0. So entire region, the left hand region represents the stability region of fourth order Runge-Kutta method. So we can conclude that the fourth order Runge-Kutta method is more better than the second order Runge-Kutta method. In this chapter we have described some numerical methods to solve ordinary differential equation. We have shown that the Runge-Kutta method is one of the good method to solve ordinary differential equation, because this method is used to solve a first order differential equation. This method is also applicable to solve a pair of first order differential equation, It can be used to solve a system of n first order differential equation. Also, this method is used to solve a second order initial value problems. Also, finite difference method is described to solve second order initial value problem as well as boundary value problem. Another good method to solve boundary value problem known as shooting method is also presented in this chapter. Three methods, that means Euler's method, second order Runge-Kutta method and fourth order Runge-Kutta method are considered to analyze its stability. And we have seen that the Runge-Kutta method of order 4 is more better than the second order Runge-Kutta method to solve first order initial value problem. Another good method known as finite element method is used to solve ordinary differential equation. This is a very good method and lot of people are working on this method to solve ordinary differential equation.